Hello Jade. This is the only bit of Trinity College that I'm allowed on at the moment. Or maybe forever, I don't mind. It's the Wren Library through those trees, and you can see people on punts going along the river. So I did think of hiring a punt, and I could punt past the library and make the video on the punt. So maybe I'll do that. You can't see the exposure doesn't come right. The porter up there is on guard at the gate, so I can't sneak in. I'm not sure I fancy wading through the moat. So this is called the Backs, and I was walking through the shopping centre, and I saw a blind man coming towards me that I knew because I remember him when I was here before. He works at the university somewhere. Don't know his name. And I was thinking about how languages work and how you describe coordinates and coordinate systems, and then it occurred to me that a way of intuitively understanding the Lagrangian as a path selection function, so that the principle of stationary action, the action is the path selection function, and the idea is it's stationary, so that on the allowable paths the action is constant at whatever part of the path the configuration lies. And the thing about Lagrange's variational calculus is that it doesn't matter what coordinate system you use, you still get the invariant of all the different coordinates, just systems of generalized coordinates that you use, is the stationarity of the action. So the physical intuition behind it is that if you think of the action as the difference between the potential and kinetic energy, these exchanges are only the ones that aren't pushed in some way. But what does pushed mean? Because sometimes the coordinate system constraints by D'Alembert's principle, they can be considered as, I think are they called virtual forces? So these forces are kind of inherent in the coordinate system that you choose. You can have an XYZ Cartesian coordinate system describing a point moving on a sphere, or you can have a theta phi, which is a longitude latitude coordinate system for the particle. So in the one there are 2 degrees of freedom, but in the Cartesian system with 3 coordinates, the degrees of freedom are coupled by the constraints that the norm, or that the radius is constant. So that gives you this coupling between x, y and z, and they have to be such that the square root of x squared plus y squared plus z squared is equal to r, the radius of the sphere. And in the completely general case, you have no idea how many coordinates there are or what the couplings are between them, but Lagrange's variational principle kind of separates out all that stuff, and you only get the paths where there isn't any kind of unnecessary wiggling going on. The particles don't kind of move without exchanging some of their potential energy with their kinetic energy, or vice versa. So all those symmetries from the conservation laws and Noether's theorem, they all hold whatever generalized coordinates you use to describe the system. So in the completely general case, you've got a whole lot of languages in which you can describe configurations of your system. And really what Lagrange's variational principle amounts to is that all of those ways of describing the configuration paths are all equivalent, so that there's always a mapping from any configuration in one generalized coordinates to an equivalent configuration in another, and vice versa. So what you have is this unspecified number of sets of generalized coordinates, unspecified number of different ways of describing one physical system. And what you're demanding is that there is some function between any pair of them, and that function is, when composed with any of the other functions, gives you a kind of lattice of translations of one system of generalized coordinates to the other, and that set of translations is all consistent. You won't ever get a different result by taking a different path through translations from coordinate system A to B to C than you would if you went A to D to C, where D is some other equivalent. So it's like an extensional sort of equality relation that holds over composition. So to make this intelligible. I think you can program these systems and program the translations between them, and you can watch how they compose, and you'll see that they always compose like that. There might be another way of starting at the top, as it were, and just specifying this as the requirement, and then teasing out different generalized coordinate systems and showing that that teasing process preserves composition. So that's the sort of category theoretic angle on the whole thing. I remembered when I first came to, this is King's College, you know. When I first came to Cambridge when I first lived here in 1992, it was around this time of year, and I used to wander around here, and I thought it was terribly exciting. It's in this amazing place. Don't know if that wow. I don't know what's wrong with the exposure on the camera. I think when you lock the exposure, the auto exposure it's not relative to whatever the auto thinks. So this is going to be an absolute mess, but maybe you'll have the audio. You have to take my word for it that this white thing is King's College, and the chapel's next to it on the left. That's the chapel, and that's, I don't know what bit of the college, but the big bit. There we go. The backs.